Normalizing Rewards to Generate Returns in Reinforcement Learning. The question is about vanilla, non-batched reinforcement learning. Basically what is defined here in Sutton's book. My model trains, woohoo, though there is an element that confuses me. Background. In an environment where duration is rewarded, like pole balancing, we have rewards of, say, 1 per step. After an episode, before sending this array of ones to the train step, we do the standard discounting and normalization to get returns. The discount underscore rewards is the usual method, but here is just if curious. So an array of rewards 1, 1, 1, 1, 1, 1, 1, 1, 1 becomes an array of returns 1.539, 1.160, 0.777, 0.392, 0.006, minus 0.382, minus 0.773, minus 1.164, minus 1.556. Given that basic background, I can ask my question. If positive returns are enforced and negative returns are discouraged in the optimized step, then no matter the length of the episode, roughly the first half of the actions will be encouraged, and the latter half will be discouraged. Is that true? Or am I misunderstanding something? If it's not true, would love to understand what I got wrong. If it is true, then I don't understand why the model trains, since even a good performing episode will have the latter half of its actions discouraged. To reiterate, this is non-batch learning, so the returns are not relative to returns in another episode in the training step. After each episode, the model trains, and again it trains well, smiley face. Hoping this makes sense, and is short enough to feel like a proper clear question.
Background. Yes, positive rewards are better than negative rewards. No, positive rewards are not good on an absolute scale. No, negative rewards are not bad on an absolute scale. If you increase or decrease all rewards, good and bad, equally, nothing changes really. The optimizer tries to minimize the loss, maximize the reward. That means it's interested only in the delta between values, the gradient, not their absolute value or their sign. Reinforcement learning. Let's say your graph looks something like this. The losses for the individual classes get scaled by weights, which in this case are Q_rewards. The loss is a linear function of the reward. The gradient stays monotonic under linear transformation. Reward normalization. Doesn't mess with the sign of the gradient. Makes the gradient steeper for rewards far from the mean. Makes the gradient shallower for rewards near the mean. When the agent performs rather badly, it receives much more bad rewards than good rewards. Normalization makes the gradient steeper for, puts more weight on, the good rewards and shallower for, puts less weight on, the bad rewards. When the agent performs rather good, it's the other way round. Your questions. If positive returns are enforced, and negative returns are discouraged, in the optimized step. It's not the sign, absolute value, but the delta, relative values. Then no matter the length of the episode, roughly the first half of the actions will be encouraged, and the latter half will be discouraged. If there are either much more high or much more low reward values, then you have a smaller half with a steeper gradient, more weight, and a larger half with a shallower gradient, less weight. If it is true, then I don't understand why the model trains, since even a good performing episode will have the latter half of its actions discouraged. Your loss value is actually expected to stay about constant at some point. So you have to measure your progress by running the program and looking at the unnormalized rewards. For reference, see the example network from Google. And search for _rollout_reward. This isn't a bad thing, however. It's just that your loss is, more or less, normalized as well. But the network keeps improving anyway by looking at the gradient at each training step. Classification problems usually have a global loss which keeps falling over time. Some optimizers keep a history of the gradient to adapt the learning rate, effectively scaling the gradient, which means that internally, they also kinda normalize the gradient and thus don't care if we do either. If you want to learn more about behind-the-scenes gradient scaling, I suggest taking a look at router.io/optimizing-gradient-descent. To reiterate, this is non-batched learning, so the returns are not relative to returns in another episode in the training step. After each episode, the model trains, and again, it trains well, smiley face. The larger your batch size, the more stable your distribution of rewards, the more reliable the normalization. You could even normalize rewards across multiple episodes.
In my opinion, the accepted answer is wrong. I read it, and I thought it was plausible, and then I stopped worrying about gradient normalization and checked something else. Only much later did I notice that it was precisely the gradient normalization breaking my training process. First off, reward normalization doesn't mess with the sign of the gradient, it's just plain wrong. Obviously, if you subtract the mean, that'll flip some signs. So yes, reward normalization does affect the sign of the gradient. Second, tf.losses.softmax_cross_entropy is, in everyday words, a measurement of how many plausible options the AI had when choosing what it did. Select 1 out of 10 actions randomly. Your cross entropy is very high. Always select the exact same item. Your cross entropy is low, because the other choices are irrelevant if you statistically never take them. In line with that, what actually does is this. If your reward is positive, it will minimize the cross entropy, meaning it will increase the chance that the AI will take the exact same action again when it sees a similar situation in the future. If your reward is negative, it will maximize the cross entropy, meaning it will make the AI choose more randomly when it sees a similar situation in the future. And that's the purpose of reward normalization. Yes, after normalization, half of the items in your trajectory have a positive sign and the other half has a negative sign. What you are basically saying is, do more of these things that worked, try something random for these things. And that leads to very actionable advice. If your model is behaving too randomly, make sure you have enough positive rewards after normalization. If your model is always doing the same and not exploring, make sure you have enough negative rewards after normalization.
If you want to support the channel, please consider liking and subscribing.